What's up, mathematicians? Justin here, and in this video we'll be looking at some applications of trigonometry. Okay, so at this point we're still going to be focusing on right triangles. We won't be looking at non-right triangles yet. And our first application goes back to that tree measurement activity. So let's go ahead and just draw out part of that. So I'm just going to draw out the person that we used as the reference object. So here we go. We have our person, and if you recall, we use the length of the shadow of the person to measure the tree. And so let's go ahead and say this person's got this shadow casting here, and we're going to go ahead and draw in that hypotenuse line. So here's a person, they have a shadow down here, and they are standing basically upright at a right angle. So there's our right angle, so we know it is a right triangle. So the person, the shadow, and the sort of the ray of light from the sun are the three sides of the triangle. Now what we want to know here is what is the angle that the sun is coming in at. So I believe the dimensions I used were 1.6 meters for the person and 2.4 meters for the shadow. Well, recall that the sine ratio is equal to the opposite over the hypotenuse. The cosine ratio is equal to the adjacent over the hypotenuse. And the tangent ratio is equal to the opposite over the adjacent. Now let's look at this particular situation and determine the opposite, the length of the opposite, the length of the adjacent, and the length of the hypotenuse. Okay, so since here's our angle, the side length opposite the angle is the height of the person. So that's going to be 1.6. Now the adjacent is going to be this length of the shadow because it's the side that's touching the angle, that's not the hypotenuse. And so that's going to equal 2.4. And then the hypotenuse, well, that's the length of the ray of light from the sun from the person's head down to the end of the shadow. It's not given to us, and it's not what we're interested in finding out. We don't care about that. So we will ignore the hypotenuse in this particular problem. And so we look here for which ratio does not include the hypotenuse. We see that it's the tangent ratio. So we know we're going to use tangent to solve this problem. Okay, so now I'm going to write it out. So we have the tangent of the angle theta is equal to the opposite, which is 1.6, divided by the adjacent, which is 2.4. And let's go ahead and find out what that ratio is. So 1.6 divided by 2.4, and that's 0.67 if we round to the nearest 100. So let's go ahead and round to the nearest 100, 0.67. Okay, well, once again, that's not the angle, it's the ratio. How do I find the angle? You have a couple options. We can look it up in our table. Here's tangent, and let's go down until we get to 0.67, and we see right around here 0.6. So it's around 34 degrees, according to the table. That's the closest, it's closer than the other two. So that means that theta, if the tangent of theta, the ratio, is 0.67, the actual angle is going to be 34 degrees approximately. That's if I'm rounding to the nearest degree, of course. And remember, we can also do this in the calculator by using the inverse tangent function. So let's say second inverse tangent, and the ratio was 0.67. And you see right here, it gives us 33.8. If we round that off, that's 34 degrees, which is what we saw here from the table. So the angle that the sun is coming in at is 34 degrees. Now, one cool thing about this is, let's say you wanted to know the time of day that you took the measurements. You could actually figure out from the angle of the sun what time it was when you took the measurements. And so, for example, this is one way that I can sort of try to see if my students are fudging their data, pretending that they're coming up with numbers, but not actually going out and doing the measurements. I could ask them, like, oh, okay, so that's interesting. That was your ratio. That's your answer. Okay, the numbers look right. By the way, what time did you go out and take those measurements? And, they might give me a time, and I can use this ratio to figure out if they were telling me the truth, if that was actually the time of day that they took the measurements. And so let's look at how we could do that. So so let's remember here that our angle of the sun is at 34 degrees. Okay, so let's switch over to the internet. And this, first I'll look at it on this page. Got a couple things to show you. So my angle was 34 degrees, and so we see that's the altitude. So this is suncalc.org, and you can enter your location. So I'm in Pasadena, California, and I can just move this thing on the top to change the position of the sun, and it'll give me the different angles and other things. So 34 degrees, so I'm going to move this until I get to 34 degrees, and you see that's right over here. Okay, so at what time would the sun have been 34 degrees elevation? And it was about 9:20 in the morning. But since the sun moves across this arc in the sky, there will be a second time when it also be 34 degrees. So let's scroll down here. Let's move it down here until we get to 34 degrees. And you see right about there. So at this would be about 4:20 in the afternoon. So about 9:20 in the morning and about 4:20 in the afternoon. So the time that I took this measurement, if I got this angle of 34 degrees, and you have to put the date in as well. It changes by day. So today is September 7th, which actually is not the day that I took the measurement. But if I took the measurement today, that was the ratio I got. I would have taken those measurements at either 9:20 in the morning or 4:20 in the afternoon. This is also, I like this site here. You can put in the longitude and latitude because it gives you this nice curve showing the angle of the sun, and also gives you a nice table. So this is, was it Keysen.casio.com/ I don't know. I just did a search for angle of the sun calculator or something like that. And this was one of the sites that came up. So it gives you the elevation angle at different times of day. So you can sort of trace it through, and you see right around at 9:20, 34 degrees. And again, down here, it was around 4:20, I believe. So that'd be around here, again, around 34 degrees. So we see that would happen between 4:15 and 4:30, which matches up with what we got at the other side. Okay. So let's move on to our second application. Application number 2. And this application will be one where that will involve angle of depression. So let's imagine this. Oops, let me move this up, make sure that I'm staying on the screen here. So let's imagine the following scenario. We have a lighthouse here, and it's on, some pier, and then we have, water, and then somewhere a ways away from the lighthouse, we have a boat in the water, or maybe you have a swimmer, a buoy, whatever, some object out in the water. So it's over there, and the lighthouse, has an observer in it, and we'll say the observer looks down at the boat and has some device, maybe a transit or maybe some other device for measuring the angle of elevation or depression. And we'll say that from the perspective of the observer, now in order to actually get an angle of depression, I need it with relation to level or horizontal, right? So we'll say that this angle of depression is 7 degrees. And then the person in the lighthouse also knows the height of the height that the observation deck is above the water level. And we'll go ahead and say that's 22 meters. So 22 meters above the water level. Okay, so the question is, what is the distance from the lighthouse or the shore, the pier, to the boat? We'll call that x. So first thing that we have to do is recognize where is our right triangle. And the right triangle, so basically what we have here is this, the base of the lighthouse gives us our right angle. We'll say this lighthouse is properly constructed at a perpendicular angle to the ground. And that's our right angle. Okay, now we need two pieces of information beyond the right angle. One of them is this 22 meter, and then we need either another side or another angle. Well, we have this angle here, but it's not inside this triangle. So that seems like it could be a problem. However, it turns out that if you have two lines that are parallel, so this horizontal line of the water is parallel to this horizontal line, you know, from the observer deck. So basically, the observer is looking straight out at a horizontal line that is parallel to the horizon for the water. And so anytime you have two parallel lines like that and then a line crossing them, the two angles that are sort of, you know, in these positions are going to be equal. We actually have a name for angles like this. They're called alternate interior angles. So alternate interior angles between parallel lines are equal. So now we see we have a side, we have an angle, and we want to find out this side. So let's, as we have done in the past, determine the length of the opposite, the adjacent, and the hypotenuse. Well, here's the angle that we're looking in relation to, and the side length opposite this angle is this side right here, 22. Then the adjacent side is the one that is touching it but not the hypotenuse, so that length is x. And finally, the hypotenuse is this length right here. I don't care about the hypotenuse in this situation. It's not something I'm trying to find. It's not something I know. So we're going to look for the ratio that doesn't involve hypotenuse, which turns out is the same thing we did last time. So we can look back up here and recall that, oh, that's the tangent ratio. So we set our ratio up here. So the tangent of 7 degrees is equal to the opposite over the adjacent. So 22 over x. And we want to find out what x is. So we do a little algebra, multiply both sides by x. And so I get x times the tangent of 7 degrees is equal to 22. And let's divide both sides by the tangent of 7 degrees. Divide by the tangent of 7 degrees. And this time I'll just go straight to my calculator. So I've got 22 divided by the tangent of 7 degrees. Now this is not the inverse tangent because we're putting the angle in and getting the ratio out. We use the inverse tangent when we're putting the ratio in and getting the angle out. So this is the regular tangent we're using here. And I get 179 meters if I round to the nearest meter. So the length, the distance from the lighthouse to the boat would be approximately 179 meters. So after seeing these two applications along with the tree measurement activity that I did a couple of videos ago, with the one where my daughter helped me out, You might wonder to yourself, do we always use the tangent ratio? What about the sine and cosine? Do they ever show up in real applications? And the answer is yes, they do. So now I'd like to show you an example from my life where I used a trig ratio other than the tangent ratio. So over the summer, one of my projects was to build a playset for my daughter. And here's a picture of the playset that I built. Now you can see in the foreground there on the right side an A-frame support brace. So basically to make sure the beam holding the swings didn't sort of swing back and forth or get pulled downwards, I put that A-frame support brace in there to keep it to keep the beam stable so that the swings would be stable, no matter how high a young child decided to swing. And so let's look at some of the calculations involved with that support brace. So first of all, okay, so this is example number 3. So first of all, I decided to put the A-frame at a 15-degree angle to the to vertical. So I didn't put it completely vertical. I put it 15 degrees out from vertical. So let's go ahead and just draw a little diagram of this. So okay. So I've got my beam, and then I've got my swings hanging from the beam, and actually I'm going to pull out this ruler here. So I'm going to draw it down 10 centimeters. Okay, so follow the dots on the dot grid paper, and we'll take it down to 10 centimeters. Okay, yeah, so I got this swing here, and then there's the second swing a little further over. So I didn't put the support brace perpendicular to the ground. I put it out at a 15-degree angle. So, by the way, one way that you can use the tangent ratio, and as you can see, I drew this at 10 centimeters. I could look at the tangent ratio and actually figure out how long this line would be instead of measuring that angle. I could also measure the angle, but why not mix it up, right? So it's a 15-degree angle. The tangent is 0.27 if I round. So let's measure 0.27 times 10, which is 2.7. That's out to about right there. So I know that this is going to come down and hit the ground right about there. And so what I'm claiming is that this is a 15-degree angle. I can take out a protractor and verify that, although running into the edge of the paper here, actually I can just do it like this. I can do from 90 degrees. So from 90 degrees, you can see that I'm right about 15 degrees off 90. It's maybe not perfect, but it's pretty close. It's closer to 15 degrees than 14 degrees. So there's my angle, 15-degree angle. And the height from the ground to the top of this beam that the swing is on is 92 inches. So the first thing I have to do is figure out what is this diagonal length. Before I can even get to the A-frame part, I have to know this diagonal length because the whole A-frame is at a bit of an angle. I don't know if you can see it in the picture, but maybe you can. Basically, the bottom of the A-frame is farther away from the swings, than the top of the A-frame. So it's coming out at a bit of an angle. So in order to find this length, well, let's determine, so first of all, where's my right triangle? And of course, my ground is assumed to be flat in this problem, and here's my right angle. So you see the right triangle there. And now let's determine if I have, let me see, I think I'll leave this space for the other half of the problem. So I'll write it right here. So the opposite, the adjacent, and the hypotenuse. The opposite length here from the angle is, I don't care. Oh, I should label the one I do care about. I care about the slant height. So that's x. I need to know this length. So I don't care about the opposite. The adjacent is this 92 inches. And the hypotenuse is x. The hypotenuse is the thing I want to know. So which trig ratio involves adjacent and hypotenuse? Let's go back here and recall. Let's see, adjacent hypotenuse, that's cosine. So I know I'm going to use the cosine here. So the cosine of 15 degrees is equal to the adjacent, 92, divided by the hypotenuse, x. So doing a little algebra, we multiply both sides by x times x, and I get x times the cosine of 15 degrees is equal to 92. And then I divide both sides by the cosine of 15 degrees. And so that gives me, let's move this up just a little bit, that the length of x is, plug it in my calculator, 92 divided by the cosine of 15, 95, I'm going to round to 95 1/4. Basically, when I'm doing carpentry, usually I'm looking for measurements that are 1/4 of an inch, 1/8 of an inch. Usually on a project like this, I won't go past an 1/8 of an inch, maybe a 1/16 of an inch. But this comes out to almost 95 1/4. So I'm going to call that 95 1/4. So that is my slant height. Okay. Now, that doesn't tell me the length of those beams, the length I need to cut those beams to. Because, you know, before I actually cut the beams, I have to go out and buy the beams. I have to make sure I buy planks of wood that are long enough so that when I cut them to the, I'll be able to cut them to the right size, right? So that's the first half. And now let's go on to the second half. Okay. So the second half, we're going to look at the A-frame part of it. And I'm not going to measure this out perfectly to scale. So this may not be to scale. I'll just go ahead and state that right at the front end. But once again, I did use 15-degree angles. So this is probably not going to be a 15-degree angle, but that's okay. We'll still have a good diagram for solving the problem. So I'll draw in my A-frame beams. Okay, so I designed it so that this whole angle here would be 30 degrees. But then we don't have a right triangle. So let's go ahead and add in that center line. Now this is not actually part of the structure, but it'll help me with my calculation. So this will be a 15-degree angle there. That will also be a 15-degree angle. And I need to know this length here, the length to cut the board to. I know that this length here, from what I did in the previous problem, is 95.25 inches. And this is at a right angle. Okay, so now I can once again write down my opposite, my adjacent, and my hypotenuse. My opposite, side opposite, I don't care about that, so I'll leave it blank. My adjacent is 95.25. And my hypotenuse is x. So once again, I have adjacent and hypotenuse, so I'll use the cosine ratio. So I'll say, okay, the cosine, and the angle here is the same, 15 degrees, is equal to x, adjacent over hypotenuse, so 95.25 divided by x. So do my algebra, multiply both sides by x. Those cancel out. And I'm going to have x times the cosine of 15 degrees is equal to 95.25. divide both sides by the cosine of 15 degrees. Cosine of 15 degrees. And I get that x is equal to, let's plug it in here. So 95 divided by cosine 15 degrees. And I get 98.61. So if I'm going to round that to the nearest eighth of an inch, that's actually going to be 98 5/8 inches, which is the length that I'm going to want to cut those boards to. Now, you may realize if you've done this kind of work that that's just past 96 inches, just past 8 feet long, which was kind of unfortunate when I did the calculations because I realized I wouldn't be able to buy 8-foot boards to do these. I'd have to buy longer boards. I did get away with getting boards that were, I don't remember, it was a little bit less. They were somewhere between 8 and 10 feet. I didn't have to go to the full 10 feet. But I knew from this calculation I would not be able to get away with 8-foot long 2x4s for the support braces. All right, so that's the end of our video on applications of trigonometry. And I hope you found these applications interesting, and I hope it gave you some idea of how trigonometry actually can be applied to situations and problems in the real world. In the next video, we'll be looking at some more advanced applications of trigonometry. Hope to see you then.